Hello everybody, my name is Faisal Ben Salah and today I will talk about study of cost efficiency in deployment of multi-protocol lab switching and MPLS deep serve. So my talk is divided into 6 parts. First I will present the topics, then we will talk about problematic. I will present next network test bed, and then I will show you results with discussion of obtained results. Then we will conclude and make some perspectives. So the objective of our research is to present first the characteristic of the architecture of next generation networks and to make a detailed study for the implementation of a core network based on an IP MPLS platform. So in this work we evaluated the quality of service performance metric such as delay variation, delay, response time, throughput for different traffic types, voice, data and video for both platforms MPLS and MPLS deep serve. The objective is to compare the performances of MPLS and MPLS deep serve using open modular tools, using the last simulation techniques, where different quality of service parameters can be measured to compare the performance of networks. Our approach in this work is to design and build an operator network type backbone to simulate a real scenario that conveys different type of traffic. The results of the work are presented according to the simulation time and the network load. The results of the comparison demonstrate the advantages over performance of MPLS network with deep serve compared to traditional MPLS networks. So, in this model, we use OpenNet modeler to compare the performance of MPLS deep serve against traditional MPLS. Two scenarios of network core configuring three application types: file transfer protocol, voice and video conferencing. We have implemented a backbone architecture based on 9 network router provider attached with 34 megabits, A3 links and 2H router and attached to the core router with E1 links. Architecture and deploy with the MPLS, deep serve and MPLS in order to make a comparative study between the two scenarios and the quality of service provided by each technology. So the traffic sources are generated by the client nodes of the object, from which to associate the application profile that present the configuration of multiple scene applications. We use the file transport protocol, voice and video on our simulation. Table below shows some characteristic of traffic. For voice over IP traffic we use the codec G711 ELO and packet load of 180 bit. We use the number of packet 1000 and 20 millisecond packet interval. For video traffic we use an average resolution of frames per second of a specific resolution set in the DCSP field to a surge for 41. The figure below shows the chosen value and parameter of our traffic model. So for file FTP traffic we use such parameters: traffic response time with light and heavy load. For video we used end-to-end delay metrics in both light scenario and with heavy load scenario, and so on for voice over IP traffic. Figure below show the FTP traffic analysis data. The MPLS response time is higher than MPLS deep serve network. We notice that the MPLS network with deep serve provides better performances in response time for FTP-based traffic. After increasing the load of the network, the response time for MPLS changed to a very high value, but deep serve remains about the same as shown in Figure 5. Then we pass on the study of network performance when traffic is the voice. We will compare between the two scenarios, MPLS and MPLS deep serve. Figure 6 and 7 illustrates the end-to-end delay parameter for light load and heavy load traffic. Then we study the performance of the network when the traffic is the video. We will compare between the two scenarios, MPLS and MPLS deep serve. Below, illustrate the end-to-end delay setting for light load and heavy load traffic. After the increase in traffic load, the result of figure 13 are evident that the delay variation has increased to a very high value for MPLS, while the variation of the MPLS deep serve delay has remained at a very low value, keeping the quality of service performances to the required level. Our results show that for all parameters discussed above, MPLS with deep serve demonstrate better performances on both heavy load and light compared to MPLS traditional network. The response time of FTP traffic on MPLS deep serve with heavy load was lower than MPLS. The delay of voice and video traffic demonstrate that MPLS with deep serve has a lower delay value than MPLS. The value of the delay on the heavy load models become much more important. The delay value for voice and video are less than 150 milliseconds according to the ICGCET standards. As conclusion, consider in our simulation that the combination of deep serve and MPLS present a very attractive strategy for the network service provider, since it makes it possible to ensure the load sharing and the quality of service demanded by the customer. However, managing this type of network is not a simple function and cannot be done manually, and it's in this sense that our perspective represents a new architecture for automation of MPLS management with deep serve based on the SDN. Thank you.